You guys have just heard how delightfully fun DCM for fMRI can be from Dr. Anderson, and you had a wonderful introduction to the reasons why you might want to use DCM as opposed to just a general linear model analysis. So I'm just going to do a brief extension before lunch over the next 20-30 minutes to explain how you can use DCM to also study EEG data. So just as a brief recap, because it's always nice to hear things a couple of times, DCM differs from, say, a classic functional connectivity analysis in the sense that you're studying effective connectivity. So functional connectivity, for the most part, amounts to just calculating time series correlations. Sometimes, of course, it's dynamic, so these correlations vary over time. But with effective connectivity, you're more interested in directed and looking at how different areas of the brain actually can cause or evoke activity in other parts of the brain. So you're looking at the influence of one neural system on another, or the simplest possible structural architecture that can give rise and explain the data without too many extra variables. And of course, after you generate your model hypotheses, then you use Bayesian model selection, as Ariana discussed, to choose the optimal model. So this may or may not be useful for you, but for me, as with my background, it's useful for me to cast DCM in think of it in this way that's similar to state space models. So state space model is essentially a series of, can be higher order, but it could also just be a series of first order ordinary differential equations. And then you also have this nice measurement model. So in this case, the x variables are the systems of differential equations. The A matrix describes the connectivity between those regions. The B describes the changes in the input, and Y is the measurement model. And then Z describes how our measurement model is changed depending on our error. So usually error models are typically that the error is Gaussian, for example. So DCM can, of course, be formulated in a similar way, where we have our equations of states as well as our observation equation. So I asked for a whiteboard. Nadia, who's in the back, it's okay, she just got in from out of town, but I was gonna draw and show you all of these fun connections on a whiteboard. It's completely okay. Now I'm off the hook, so I can use that as an excuse. But I was gonna draw out an example of how you have different regions and how you can just have nice parameters that describe what's leaving, the sum of what's leaving and the sum of what's entering the compartment, and how you can have these modulatory effects. One of the things that's kind of interesting is some models, like for example, just a single compartment model. If you have just one region of interest, there's some information coming in and then it just dissipates, it just leaks. Then, and you have nothing else going on, no balloon model, nothing else, then you can solve this analytically and it just amounts to an exponential decay. So this is something that comes out quite easily, and you can very easily estimate what those parameters are that describe the exponential decay. Sometimes, if you don't have measurement in all of the compartments, which we do in fMRI and EEG, but sometimes you don't, and in that case it becomes very difficult to have a way of estimating all of the parameters, and sometimes you can't. And so when you can't, the model is said to be unidentifiable. But most models can be approximated numerically even when you don't have an a priori identifiable model. So I was going to talk about this a little bit, but it's okay. I'm off the hook. So this actually is an example of something that came from my PhD work. So you guys heard Tal Yarkoni talk yesterday about this fictitious study about bad pandas, or maybe it was 2 days ago. And he was saying, this is my magnum opus, and this was my entire dissertation work, and then he never got it published. And I was thinking, me too. And then he said, oh no, that was just a joke. This was a fake study. And I was like, oh, now I felt like the sad panda at that moment. But it was kind of funny because one part of my PhD work used compartmental modeling using systems of differential equations to model manganese transport throughout the brain, because manganese inhalation, not too much, if you eat, you can eat a lot of manganese and you're okay, but if you inhale it, it can actually cause very similar disease to Parkinson's. So, but unfortunately, for various reasons, that one aspect of my PhD was never published. So I felt the angst of the bad panda, but in any case. So this is a simple aspect of what you would get solving for DCM. So just a couple of quick notes about how DCM for fMRI and EEG differ. Essentially, the overall framework is quite similar, but not all hypotheses are suitable for DCM testing, so it's possible to come up with models that are very, very similar, and it's difficult to distinguish between the two. The other thing is that model comparisons are only valid if the data are identical in all of the models. So you have to use the same data if you're going to do model comparison. One aspect of fMRI is that the number of ROIs that you consider in your model should all be the same. So you shouldn't have different numbers of ROIs, but for EEG, if you're not sure how many regions that you want to consider, you can actually vary that. And so the model selection can be used to determine which sources should be included in your model. So once again, the general framework is we create a series of candidate hypotheses between regions and how these areas causally affect each other. We perform model inversion using variational Bayes, and then we select the model with the highest evidence using Bayesian model selection. So yes, so the overall concept is the same as what Ariana spoke about, but the observation model is different. So with fMRI, we're interested in modeling the hemodynamics using the balloon model, but with EEG, we have to think about what we're actually measuring, and so the state variable model is a bilinear state model, of course, for fMRI, but with EEG, depending upon which model you use to describe the neurons in a particular cortical region, as well as this lead field model is what's involved with the measurement. So what do I mean by a lead field model? I think this has probably come up so far in the course, but I'm not sure. With EEG, you're making measurements, or MEG, but with EEG, you're making measurements on the scalp, and you can use this process called the inverse approximation to try and estimate where the underlying sources are in the cortex that are driving the measurements that you're recording on the scalp. And so even after you've created this biologically plausible model of the dipole sources, you still have to filter that through the lead field model in the end, because that's actually what you're measuring. And so both of those layers are involved with DCM for EEG. So just a few considerations when you're thinking about running a DCM for EEG study is you might want to first consider, will I be modeling evoked ERPs or steady state potentials? Are you going to be looking at, for ERPs, you're most likely interested in a time domain analysis, but you could also take a look at frequency domain or cross-spectral densities. And then there's this other thought, which neural mass model or neural field model should I use in the modeling? And then some of the questions you can ask is my effect driven by extrinsic or intrinsic connections? And I'll show you some examples of what this means. Which neural populations are affected by contextual factors? Which connections determine the observed frequency coupling? And how can changing connections parameters influence? How does that influence the data? So this is just an overview, and this slide, as well as a couple, have been borrowed from Richard, who is at the Phil, and this is from the SPM course in May 2016. So at the beginning of the analysis is you choose what he calls your hardwired model features. So that's what I'm calling the neural mass or the neural field model. So as Logothetis mentioned, it's very difficult to define a canonical or basic elementary unit of neural computation. But you can still make some interesting models that are biologically plausible at certain levels of abstraction. So there's this one by Janssen and RIT in 1995 that's been very influential in later evolutions of neural mass models and neural field models. So what they did was describe the dynamics of cells within a cortical column using 3 different subpopulations. So inhibitory supragranular cells, excitatory spiny cells, and excitatory pyramidal cells. And the nice thing about this is that we have different laminar layers of the cortical column that are described. And so this is particularly important later in some of the later evolutions of this model, because if you're interested in looking at different frequencies, we know that higher frequencies tend to be more prevalent in the superficial layers, and lower frequencies tend to emerge from the deeper laminar layers. And there's also asymmetries about the information being sent and received from those different laminar layers in terms of the frequencies. So Olivier David and Friston extended this in 2003, and it's also been extended further in later years. So this type of model is the generative model, which is used to describe what we're actually measuring. And so this model is kind of underneath the lead field model that I talked about, where you estimate the sources. So on the left, we have a typical neural mass model, and on the right, we have the canonical microcircuit model, which is a mean field model. In DCM, this example of the neural mass model is implemented with this function SPM FX ERP, and on the right, SPM FX CMC, canonical microcircuit. So what are some key differences here? So the neural mass models use these sigmoidal operators to transform the membrane potential to an average population firing rate. So in that sense, the sigmoidal operator makes these models nonlinear. You also are primarily interested in just the first order statistics, so you're essentially looking at the dynamics or the interaction between population means. There was also an extension, Rosalind Moran extended this to what she called the LFP model, so that's implemented in SPM FX LFP, and that particular neural mass model is useful if you're interested in studying steady state responses in spectral densities, so frequency domain steady state responses. The canonical microcircuit model is an extension to this, and it looks at higher order statistics, and it can provide, of course, a richer description of biology through additional parameters. So of course this comes at the expense of now you have to estimate more parameters, but you do also get a richer description of what's happening. So in this case, conductance, currents, time-varying currents, and ion channel dynamics are considered in creating these models. So these models, you've all probably heard of the Hodgkin and Huxley models, where they use these circuits. I have this circuit at the bottom here where you have capacitance across the membrane and different resistors in parallel to model a neuron. And so those types of circuit models by Hodgkin and Huxley and later by Morris-Lacar are kind of the inspiration for this later canonical microcircuit model. So again, this is just showing the evolution of how the canonical microcircuit model has evolved over the years, starting with the Douglas and Martin 1991, and then moving up later to Dimitri Pinotzis model in 2012. So the canonical microcircuit model has 4 different subpopulations of neurons that it considers. Each is interconnected with some descending and ascending connections. So these are the intrinsic connections, and they also influence their own activity through these loops. There's also forward extrinsic and backward extrinsic connections. So intrinsic connections are connections that are modulating the internal measurement of this particular location or this particular source in space. The external extrinsic connections are the ones that go off and influence other sources in space. And the exogenous input comes in at the spiny stellate cell laminar layer. And then what we're measuring here is this parameter P3, which, as you can see, comes from the superficial pyramidal layer. And this L term here is the lead field, as I mentioned, from the solving the EEG inverse problem. So this is just another formulation of the canonical microcircuit model. So what you'll see here is that this is from a review paper by Rosalind Moran, where we have those same cell types and the same equations, but in this case they're formulated as second order differential equations. But there's this nice trick where you can just set one variable equal to the derivative of another, and so you can take one second order derivative equation and break it out into 2 first order derivatives. So this makes it useful when you're using the solvers based on the Taylor series, like that Dr. Anderson mentioned, just using the Euler method or anything like this. That would be the simplest. Okay, so briefly, if you're using DCM for EEG, if you want to specify, for example, the CMC model, then you choose, and you're studying ERPs, then you first choose ERP and then choose that you're interested in using the canonical microcircuit model. But of course, there's a number of others listed here that you could choose. You could choose the LFP model that I talked about, or other more specific bespoke models that they've developed for different purposes. And these are always changing, and they're always adding more and more of these models to the DCM software. So now that you've chosen your hardwired model features, which aren't exactly hardwired, but they're estimated, of course, in their parameters. But that's once you've chosen your measurement model, then you then want to build the connectivity architecture. So you can have a number of different hypotheses. They could be, do we have 2 regions involved or 3? And then you can have extrinsic modulation, where there's modulation between the different regions, or intrinsic modulation, where perhaps the coupling between a specific area and itself actually changes as a result of a task. So when you're specifying a particular model in DCM, you first want to specify the forward connection, or first the inputs. And here's an example you can click through here as how you'd implement just using these buttons and what these mean in terms of the connections. So inputs, your forward connections, your reverse connections, whatever your modulatory hypotheses are. And then you can have different factors that can influence the connectivity. So this is how you build your different model hypotheses. So here's an example of 6 different model hypotheses that were implemented in DCM using the ERP and also the straight neural mass model based on, I think it was the Olivier David paper from 2003 or 2005. And this is done by Marta Garrido, where she studied the different interactions that occur during a mismatch negativity experiment. So this is just quickly a typical workflow for DCM for ERP. You may want to downsample your data, not necessary, but you may want to just for numerical considerations. Then you want to filter your data, probably pick an upper limit that's related to the line noise. Then you want to epoch your data, remove artifacts, average, and then come up with your source estimates. So you don't have to do this exactly like this, but this is a classic way of analyzing EEG data using SPM for EEG analysis. So now that you've chosen your measurement model and you've built your different model hypotheses and the different structural architectures that you're going to test, then you want to fit your model parameters to the data. So this essentially amounts to, in the software, if you're using the graphical user interface, it amounts to pushing this button called invert DCM, and that will perform the parameter estimation for you. And so this crazy graph here is just showing you an idea of, if you're looking in, this would be, I guess, three-dimensional parameter space, and you're trying to find a minimum, something that minimizes the difference between your model prediction and the measurement, then you would try and find a trough, I guess, or a sink in the parameter space. So if you were going to do this model inversion in the spectral domain, this is a very simple example of how you could take state equations and transform them into the spectral domain. So I show you up above, once again, just the classic state space model. You have coupled ordinary differential equations, and then your measurement model with some error. You can quite easily just take the Laplace transform of this. So the derivative with a Laplace transform is just multiplying by s. And then you can rearrange terms, and then you can get a new form for your transfer function in frequency domain, in the frequency domain. And model inversion in this case tries to optimize the parameters that best describe the cross-spectral densities. So now after you've clicked that invert button and all of these lovely screens pop up showing you how the parameters are being estimated, you then want to check your data, make sure that your ERPs, for example, actually do differ in two different conditions. You want to check your sources and make sure that those look appropriate for what you would expect. And of course, consider your model with respect to the hypothesis that you're actually interested in testing, and the inferences that you're looking to make based on your model. And sometimes you want to rerun the model. This might be if you have a stubborn subject, for example, that's not converging. You might want to change the priors. Most of the time, the default priors work quite well because they're based on physiologically motivated intervals. But sometimes for a particular task, or maybe for a particular subject population, like Ariana's studying Alzheimer's disease, maybe their physiologic parameters are slightly different. So if necessary, you might need to relax some of the how stringent your priors are to allow a little bit more movement, or maybe perhaps just shifting them a little bit. So you can sometimes, if you get it to work for one subject, use those priors on other subjects, for example. So then the last step is picking the best model. And so Ariana has already talked about the Bayesian model selection procedure, but essentially you're trying to choose the model that describes the specific, the data as best as it can without additional complexity. So choosing the model that best describes the data while also considering the complexity term. So this is actually kind of similar to, if you remember, I talked about regularization with machine learning yesterday, where you can add this penalty term for complexity. So DCM has this nice trade-off between accuracy and complexity as well, so that you do favor the simpler model that also describes the data just as well, or almost as well. And so just as a rule of thumb, I've heard people say that you want a Bayes factor of, say, at least well, more than 3, so higher than 3, hopefully as high as possible when you're comparing and choosing the model that works best. So 1 to 3 is weak evidence for one model over another. So these values are all relative, so what you're doing is comparing, of course, the model evidence for one model versus another. And this is just a quick note here. I was lucky enough to go visit Carl's group, and I had so much fun in London and visiting this whole group. And I was able to work with someone named Gerald Kure and also Biswa Sengupta. And Gerald, we've published this nice paper on Bayesian belief updating. So we were interested in using DCM EEG to study seizure dynamics. But what we had was not repetitive trials. We didn't have 100 trials to epoch and then average. We just had this long recording where at some point someone would have a seizure. And so we were looking to model how not just the seizure itself and not just the time before, but really how the intrinsic and extrinsic parameters changed over time leading up to the seizure. And so it's really difficult to get one model to converge for all of this, especially because the parameters themselves are changing in the different conditions. And so there's this nice procedure where you can update the parameters and do your estimation over time in different windows. So in this case, the posteriors from the previous window are then used as the priors in the next window that you're estimating. So I thought that I would mention this in case anyone else has kind of these long data recordings that they're trying to model. And that is exactly the 30 minutes that we're right before lunch. Just a quick overview of DCM EEG.
Criteria for a successful talk, exactly 30 minutes. Questions? For both Ariana and Pamela, of course.
Thanks. Great talk for both of you. I have a question for the EEG part. I was wondering if you can comment a little bit about the source localization. Actually, I have a few questions, but I'll start with this one. If you can comment a little bit about the source localization, the spatial registration that you are actually inferring while you're doing DCM EEG, because I've never done DCM with EEG, but I know that all the other software like Field Trip, EEG Lab, the other that are available are usually more like, they're not really inferring that much. So they're doing just correlation in terms of frequency. And this seems to be the only one that is like inferring a lot. So I know that it has been criticized a little bit about this. So if you can, comment a little bit. And
yes, so has it not come up in the class yet? I'm surprised if EEG inverse, it hasn't. Okay, so what happens in just a nutshell is you first have to create this forward model. So you have to create a hypothetical set of measurements that would occur if you had a dipole at a variety of different places in space. So if you have a dipole at a specific location, you have what's called again, it's another forward and a reverse model, but you have a forward model of how that dipole propagates through the different cortical layers and different parts of the brain, and how that would theoretically be measured on the outside. So one of the toolboxes that I've used for this is OpenMEEG. There's a nice paper by Alex Gramfort describing how the sources are modeled and propagated in this forward model. So then the reverse part of it, there's a lot of different algorithms for that. There's beamformer, there's all different types of models. With DCM, they have, I think it's a paper by Matut, I want to say Matut, maybe 2009, I think they're still using that version. But there's a lot of different ways of choosing the sources as well. And one of the big factors involved is how specific you try to make that forward model, that first step. If you try to make the resolution really high, then you have a whole number of potential true locations of where the source is coming from. And you can imagine this as a number of equations with a number of unknowns. So the more densely you pack the hypothetical sources, the more unknowns that you have, and the more rank deficient, and the more ill-posed the problem becomes. So if you have something that's a little bit more coarse, it's a lot easier and faster to make the estimates. And so, and of course, if you have more measurements on the scalp, those are the knowns, if you will. And so if you have more electrodes on the scalp, then you're given more information. If you have, say, 30, it's hard to make very specific estimates. I've heard a lot of people say 100 is good, something 100 or more. So, is that useful?
Yeah,
Okay.
absolutely. Can I make the second one?
Yeah.
General, both for EEG and fMRI, like when you are estimating your parameters with the BMA, and usually you look at A, B, C, and then you can compare between groups or whatever. Does have any sense also to look at A and B together, or the effect that you can have, like both the endogenous connection, the intrinsic connection, and the plus the modulated by the task, or not?
I think I kind of missed that first part of the question. Could you? So you're saying that you're trying to distinguish between an intrinsic and an extrinsic?
No. I'm saying, like usually in the end you look A, B, and C, and then you can compare and do whatever between groups. Does have any sense also look at A plus B or times B, like together?
My intuition that would be that those are confounded because your B already incorporates the information of A into it. So it'd be hard to parse those two apart. I don't know if you have a different take on it, but
I guess I'm not sure what A and B are in this.
So
A is the initial connectivity matrix that describes the structure, and B is the modulatory matrix. Okay.
depends on A.
Well, so
because this is something usually I've seen in the paper just A, B, and C separate, but something that like a review asked me in a paper, and it was really like, can I do it or?
So I think this is what I was going to try and show, which is that there's this funny thing that sometimes when you add nonlinearity, when you add a B, an influence to a model, the model actually can become identifiable or more identifiable than it would be. So you can have a model where there's no modulation and you can't solve it analytically. That doesn't mean you can't solve it numerically, especially with some Bayesian priors. But if you add nonlinearity to it, you can actually solve analytically. So sometimes adding a modulatory effect can actually improve your ability to make parameter estimations.
Okay, thanks. The very last one, very quickly, and then I leave you the mic to anyone else. I don't know if you already mentioned this in the EEG part, but I know that like recently has been developed the DCM also for the resting state part for the fMRI. Is it possible to do it also for the EEG?
I don't know. I mean, I would assume that the answer is yes. I don't know what the status is of that development. I know that
I've checked on the literature and it seems that there's nothing, but I don't know if you knew something.
I don't know about resting state per se, but you can do steady state EEG analysis, and then you can of course take a look at that over time if you use Bayesian belief updating. So I would think that you could do it. Yeah.
Thanks so much to both of you.
Hi, I have two questions too. It was mentioned that the PPI is it functional connectivity or is it effective connectivity? Because I thought we cannot really infer the directionality of the connections out of the PPI. So that's my first question. And second question is about DCM. So to my knowledge, we can only compare the models that we want to compare. So apparently DCM is a really complicated model. And so even though we have 10 models in hand, I guess like, maybe model A is the best one, but it could be, I'm just wondering, it could be, maybe the least worst one. And I wonder if when we make models, whether they have to be driven by some theoretical, like literature or background, or or if you have any practical like suggestions how to use DCM, it would be great.
I'll take the second one.
Okay. So I believe the PPI is just a single region DCM. So you are looking at the how do I say this? The intrinsic connectivity of the region within itself. So that would still be included.
In terms of the second question, I would say that you always want to have a hypothesis at the beginning about the question that you're trying to investigate and really think about what it is that you're trying to assess with DCM. Of course, it's possible that you're finding a local minimum or maximum as opposed to the global minimum or maximum, not just with respect to the parameter estimation, but also with respect to what you're saying in terms of testing the different structural architectures. So I don't think that there's an exact answer to that, except that if you're doing it with, if you're using fMRI with EEG or fMRI, you typically don't have too many regions that you're considering. And so I would guess that if you're thoughtful about the structural architectures that you use as your hypotheses, that you'll probably come to an answer that's one of the best answers. Yeah.
Hi, thank you for the great talk. So I also have question on the DCM on fMRI. Could you comment on the recently developed spectral DCM that is applied on the resting state? I wonder if we can gain some novel insights if we can combine the classical DCM and the spectral DCM.
I'm actually not very familiar with the spectral DCM technique because I've never used it before, but do you have any? No.
I'm not familiar either. When you say spectral, is it for fMRI? Is that?
I believe so. Yeah.
Oh, is it?
Stochastic?
Yeah.
Is it the stochastic one?
It's actually implemented in the SPM12, and I believe it's developed by Carl Friesen team. Yeah.
I've never used it before, so I can't give any insight on it. I believe I was there when they were developing it, though, and it sounded like it was going to be very useful, but I haven't really looked into the nuts and bolts of it, so I don't think I can comment on it with any sort of authority.
All right, thanks.
Have you or others seen any advantage in using non-parametric whole brain analyses before running DCM? Because you mentioned GLM as a prerequisite for it.
That's also something else that I've never tried. There's basically a formula behind this, and there really shouldn't be that much improvement because although the GLM certainly does have its limitations, the final analyses on the DCM is not built upon, for example, the level of accuracy on a voxel-wise scale because you're looking at regions of interest. So you would expect that even if you did some sort of non-parametric analysis and you found slightly different regions you wouldn't find slightly different regions. You might find like slightly different intensities or anything. You'd expect the results to be similar enough that it probably wouldn't affect a DCM, but perhaps it might. It would be hard to think of, though, an instance where the deviation would be so large that it would be an entire region that would be missed, which is what DCM depends on.
Hi, thank you for your talk. This might come from the fact that I don't know some of this math, for sure. I don't understand why you say that DCM is modeling at the level of, at the neuronal level, or saying it differently. All models are trying to do that. I mean, who cares about bold signal in a sense? We don't, that's a measure that we have, and that's perhaps a limitation of all the models, but all models, GLM or not, want to go at the neuronal level. So I didn't understand why that's a major difference between GLM and DCM.
I think the difference is because when you state the model in a DCM, what you're doing is you're going back and doing a Bayesian estimation on the model parameters for the neural dynamics. You're not doing, for example, when you're working on a GLM and you get out your analysis, you're getting out a beta of the actual voxel activation with the expected time course. So your estimation is actually on the observed bold signal. Whereas when you're doing a DCM, because it's Bayesian, you're going back and the actual parameters underlying the model. So I think that's just the key difference. I understand what you're saying. They all are built upon this assumption of some sort of neural activation, but which parameters they try to estimate and which level they try to estimate it is where they differ. And that's because one is Bayesian, one is frequentist. Do you have any other thoughts or any other questions?
Yeah, I had a similar question Young had. So would it be advisable to create a lot of models to not have that problem of basically looking at the least worst model?
Sure, I would say go ahead. In fact, maybe even create a family of models to test between different groups. So with EEG, if you're wondering whether or not to have 2 or 3 different sources involved, you might have a couple of different candidate hypotheses for 2, a couple of different candidate hypotheses for the different modulatory effects for the 3, and have these different models to determine which one is the best. Yeah. So.
I just wanted to add something to this question. Maybe DCM is not the best approach if you're exploratorily looking at data. You should always focus on a question you have beforehand, where DCM is suitable. So you already know, or you already have probably some kind of idea of what models you want to compare, and then DCM is a really good approach. If you're exploring your data and you don't really have an idea of a model and you're using a lot of models, maybe DCM is not the best approach to go for.
I guess I just want to expand a little bit about that earlier question. Is you're not using a canonical HRF, right? So in that single compartment model that I showed you, the measurement model was literally manganese. There was nothing in between. There was nothing between the manganese and what we were actually measuring. And so exactly what Dr. Anderson said is that the parameter estimation goes right back to the balloon model, or it goes, what's driving the measurement is the parameters that are changed are within the measurement model that's biologically plausible. So the things that are tweaked within the EEG situation, for example, would possibly be the weights that connect different laminar layers and see how those affect the measurement. So I don't know if that helps a little bit.
So I'm actually going to go ahead and interrupt because our talk by Jim Paxby is in a different moment, so we have to leave a little extra time in order to get there. And I want to make sure you get a chance to speak back so you have the energy to listen to more talks. So thank you, Ariana.